Hi, welcome back. This is 1.3 in college algebra. So we're going to be taking a closer look at graphs and picking out some characteristics which we will need to identify. And yeah, so let's take a look. So 1.3, this is basically just more on the graphs of functions. And if you kept taking math, you would see a lot of this stuff explored in much more detail in calculus. Okay. The first characteristic we kind of put our eyes on, increasing versus decreasing. So is it going up or is it going down? So in layman's terms, I guess. Okay, so more than just saying, is it going up? We'll have kind of an algebraic definition. Okay, so let's take a look over here maybe at what's going on. So we'll say we have one point x1, the first one we see, and then the second one we see x2. For something to be increasing, that would suggest that the point x1 is lower than the point x2, right? So maybe we have some sort of curve going like that, or a function going like that. And this is f of x1 and f of x2. So what's the relationship between f of x1 and f of x2, given that x1 is less than x2? So if x1 is less than x2 and it's increasing, then it must be the case that f of x1 it will be less than f of x2. Okay. Then likewise decreasing. Definition, if x1 is less than x2, then you can kind of guess the relationship between the heights, right? So in that case, it'll be kind of this other scenario. If you're looking to the right there at the top of the page, it's going down, right? So decreasing, going down. So if x1 is less than x2, then f of x1 will be greater than f of x2. Right? Okay. The third sort of thing then, what about when it doesn't change, right? So if it's constant, we'll say. So it's constant if f of x1 equals f of x2 for all x1, x2 in some interval. So a constant function would be basically horizontal in a particular interval. So you could draw a little picture if you wish, something like that, right? Okay. Right. So in the homework, they'll give you basically a graph of some sorts. So let's take a look at like a parabola. So 1, 2, 3, there's a dot there. And then at -1, 1, 2, 3, 4. 2, 3, 4, there's another dot. And then at 0, 3, there's a dot there. And then at 1, 0, there's a dot there. And here's our graph. Okay, so basically an upside down parabola. Okay, so they want to know the open intervals of increase and decrease and wherever it's constant. Okay, so it's increasing or going up from -infinity to this high point right here, which is the vertex of the parabola. Okay, so it's going to go from increase from -infinity to, I guess the x value there is -1. And you could, the pictures, you know, you click on it and zoom in, and you'll be able to tell exactly where that point is. Okay, and it's an open interval, so they don't want the bracket; they just want the open interval. Okay, so it then decreases from that point on. So then it starts going down, right? So that means decrease. And there on the blue, I put it in blue. Okay, so decrease from -1 to forever. And then is it, no, it's never really constant, so we'll just write no. Okay. Let's look at another example. Okay, so this one's a bit more funny. Let me use some color. Oh, well, first off, there is a point at 2, 4. 2, 3, 4. It's right here. Okay, so I'll draw the graph in yellow. So it's going like this to 0, 0, and then it pops up like this. Okay. Okay, so same question. Find the interval of increase, decrease, and constant. Okay. So where does it seem to be increasing? Well, from 0 on, right? So if I'll do that in red, drawing over it here in red, on and on, it's going up from 0 to infinity. Okay. Where is it decreasing? Well, never, right? It doesn't seem to be decreasing anywhere. So I'll just write no. And then constant. So it looks like it's just staying the same, or it's horizontal from negative infinity all the way up to 0. Okay. So we'll put that in there. Negative infinity to 0. Okay, and that's the idea. Okay, so it's going up, down, or remaining the same. The next concept we want to work with relative max or min. So section 2. So the deal here is you may have some sort of graph that you're working with. Okay. And maybe it looks like this, and it goes down maybe, and then it goes maybe up, and then it goes down again, and maybe it levels off and does something like this. Okay, so imagine this represents a profit function. Okay, so the y values represent the profit, the height values, and you're trying to maximize your profit for units sold. So maybe if you sell 2 units, you have negative profit, so you're losing money. 3, but if you sell 4 units, you have this max. You have this the top of a hill right here. So you think of it like a max. Okay, so there's a maximum there and a minimum over here. There's also another minimum, kind of, and that's what they mean by relative. Okay, relative to a certain area, there's a maximum, or relative to a certain area, there's a minimum. So if I, let me put this in blue, if I sort of just limit myself to this box right here, then the minimum is at right here, and the maximum is right here. Okay, so relative to this box, there's a minimum max. Now, clearly, there's also this idea of like a global max or global minimum, which you may or may not need, right? So if you're talking about units sold on the x-axis, you would never sell a negative number of units, and so this maximum to the left, where the numbers are negative, so I put this maybe in red over here, you don't even consider that, right? That's not really even part of the picture. This is just kind of extraneous junk. So you'll have to develop this idea of a relative max and min, and that's what this section's about. Okay. So let's dive in here and give this some formal definitions. So relative max. What do we have? F of A is a relative max if there exists an open interval containing this point A, such that f of A is greater than any f of x in that interval. Okay, And then we have the relative max, which kind of has the same sort of definition. Oh, sorry, relative min now. So, you just rewrite that definition. F of A is a relative min if there exists an open interval containing A, such that F of A then is less than F of X for all X not equal A in the open interval. So let me write that. F of A is a relative min if there exists an open interval containing A such that, that ST means such that, sorry if you didn't catch that, such that F of A then is less than F of X for all X not equal to A in that given interval, in this open interval. Okay. And of course, if you can't read my handwriting, but these definitions are in the book. So, okay. Let's take a look at an example. So we'll just look at the cosine function. F of X equals cosine X. Oops, I put cosine T. Sorry. Okay, so here we go. So let's put some tick marks on here. I'll go by pi over 2's. And the cosine function, has a max at -1, a min at, min at -1, a max at 1, and it has this kind of shape to it. Oops, over there, over here, and down, and back up. Okay, so it has an infinite number of maxes and mins, but we're going to kind of just restrict ourselves in a certain interval. So we just want to look at from, how do I want to do this? From negative pi over 2 to 3 pi over 2. Okay, so in the open interval from negative pi over 2 to 3 pi over 2, we'll talk about these maxes and mins, right? So F has a relative max at, well, in this interval, maybe I should, on the number line, put some tick marks here. So there's negative pi over 2, and here's 3 pi over 2. So in that interval, F has a relative max at 0, right? So at X equals 0. So what is the relative max? That's just the location. The relative max is F of 0, which, cosine, its max is at 1. What about the min then? So F has a relative min at, well, you look at the graph, it's at pi, right? So when X is pi, that's the location. And then the actual value of the minimum will be F of pi, which of course is then -1. Okay, so that'll be used in minimizing and maximizing functions in certain ranges, depending on your application, right? Okay, so some other characteristics of graphs, symmetry. So 3 types we'll focus on. There's the x-axis symmetry. So basically it says if you have this point xy on the graph, you will also have this point x negative y. Okay? And that just means x-axis symmetry. Then, of course, we'll have y-axis symmetry if when you have the point x comma y on the graph. You also have the point negative x comma y. Okay. And that'll be y-axis symmetry. And then origin symmetry if you have the point x comma y on the graph. You'll also have the point negative x negative y on the graph. Okay. So that would be your origin symmetry. Okay. The test for determining, I mean, if you can't graph the thing, and a long time ago, obviously, we couldn't graph these things. We have some algebraic tests. And even if you do graph it, something can look symmetric, but then when you kind of really get into the finite details, or into the the nitty-gritty details, it turns out it's not symmetric. So you want something better than just your eyes to kind of guess the symmetry. So we have these kind of algebraic methods, and the methods we use are kind of suggested by this introduction graph things here. Okay, so these pictures 1, 2, and 3. So in picture 1, the test comes from the fact that if you have x, y, you'll have x negative y. Okay, so what you're going to do in your relation or your equation is replace y with negative y. And then if the equation doesn't change at all, then you know it'll be x-axis symmetric. So let's try one of these. Okay, so example, we want to check the graph. Sorry, my pen is. Check y equals x squared minus 1 for symmetry. Okay, so I'm not even going to graph the thing. I'm just going to use these algebraic methods. And if I give you a test, I would expect you to do this kind of test. Okay? All right. So for x-axis symmetry, then, if you look at the picture 1 above and to the left, it's x, y, x, negative y on the bottom. So in the equation, I'm going to replace y with negative y. Okay, and then see what happens. So I have negative y is x squared minus 1. And then I try to manipulate this equation to put it into the original form if I can. So the original form has positive y equals. So I can try to multiply both sides by a negative 1, but I end up with negative x squared plus 1. Okay, so that's not the same as the original equation. So you compare and contrast. So therefore, I'll say this does not have x-axis symmetry. Okay, so for y-axis symmetry, look at graph 2 above here. So it says I have xy. If you have xy on one side, it will have negative xy on the other. So that suggests replace x with negative x and see what happens. Okay, so that's what I do. So I have y equals, instead of x, I have negative x squared minus 1. Okay, and I simplify it and try to manipulate it or whatever. Negative x squared is negative x times negative x, which is positive x squared. And again, I compare it with the original. So is that the same? Oh, yeah. So it has the y-axis symmetry. Okay. Then finally, origin symmetry. Okay. So our graph this time tells me to replace xy with negative x, negative y. You see graph 3 there. Okay. Okay, so I start replacing things. I have negative x here, or negative y there, and then negative x inside here. And then I try to get it into the original form. So x squared minus 1. Multiply both sides. Oh, so that one's not working, right? Okay, that's definitely not the same as this thing. So, no. And so therefore, the only kind of symmetry it has is that y-axis. Okay, let's look at another. F of x equals x cubed minus x. And let's look at x-axis. Okay, so again, in picture 1, x-axis symmetry, you're replacing y with negative y. Seeing what happens. So the f of x is the y. Okay, so I'll have negative y instead of that f of x equals x cubed minus x. Then I try to get it in the original form, multiply by negative 1 on both sides. And compare, and no, that's not the same. So no on that guy. let's try y-axis. So I have y equals, now I replace x with negative x, right? So y negative cubed is still negative, so I have negative x cubed, and then negative negative is plus. Is that the same? No, that's not the same. Okay? The signs are changed. And let's try origin. Okay. So I'm going to replace x and y with negative x and negative y. So I have negative y on this side, and then negative x over here. Okay. And you try to rewrite it so it looks like the original, if possible. You can multiply both sides by a negative. That won't change anything. And is that the same as the original? Oh, yeah. So this time it seems that it has origin symmetry. Okay. So you're going to have to do these tests on the test. When I give you a test, I expect to see this. So don't just graph it and say, ooh, I think it has origin. No. Okay. You have to do these algebraic tests because in the real world, the graphs may lie, right? They may not be perfect, and we need perfection. Okay. Okay. Anyways, associated then with these symmetry types, or the even and odd symmetry, and you know, the second graph there is the even symmetry. So y-axis symmetry is the same as even symmetry, and then origin symmetry is odd symmetry. Okay, we don't consider the x-axis symmetry because we're dealing with functions, and you look at graph 1 there, that's not a function because it fails the vertical line test. Okay, so that's why when we deal with here an even and odd, you're not seeing that other kind of symmetry. It's just the even is the y-axis, and then the odd is the x-axis. Okay. They use different tests for these, and I prefer if you use these other tests as well. In particular, it'll help you with your algebra. So if you kept taking math, the algebra is basically the language of math. And if you can't do the language, the basic language, you're not going to get very far. So this will give you a lot of practice doing algebra. Okay. So anyways, even symmetry, to do this, you have to consider f of negative x and see if it's the same thing as f of x. Okay. So for example, if we have the function f of x equals x squared minus x to the fourth, I'm going to consider f of negative x. Okay, that's where I start. Okay. Okay. So I replace x with negative x wherever I see it. So negative x squared minus negative x to the fourth. Okay. And then if you raise a negative to an even power, it becomes positive. So this would be x squared minus x to the fourth. And that is f of x, right? That's just this thing right here. So I can write that equals f of x. And so I've shown that f of negative x, so thus f of negative x equals f of x, okay? Which is going to imply it's an even function. Hence, even, right? Okay. Let's look at another example. So here we have f of x equals x times the square root of 1 minus x squared. So in general, if you have a polynomial, you can kind of just look at the degrees. If the exponents are all even for a polynomial, then the function itself will be even. If the exponents are all odd, then the function itself will be odd. The problem is you'll have problems like this example I just wrote, where it's not a polynomial, okay? So you can't pull that trick here. You have to do the test, okay? There's no way around it. So see what f of negative x is. So I'm replacing x everywhere with negative x, so square root of 1 minus negative x squared. And I got negative x times the square root of 1 minus negative x squared is just x squared. Okay. And then what is this? Well, this is just a negative times f of x. Okay. And that turns out to be the test for oddness. Okay. So the other test, which I neglected to write down, is odd if f of negative x is equal to negative f of x. And that's what we just got. Okay? So here, in all of this jazz, we noted that f of negative x is equal to negative f of x, and hence it's odd. Okay? Okay, so, again, the point is you can't just look at it and say, ooh, the degrees are all even, so therefore it's even, or the degree of the polynomial, it's all odd, so therefore it's odd. You got to do this test, okay, especially for these cases where you're dealing with something that's not a polynomial. Okay, so anyways, there's that. Piecewise functions come up a lot in applications. Piecewise functions, especially if you do electronics, you're gonna run into these things sooner or later. Piecewise functions, and we'll just begin with evaluating them. So here's an example. We have f of x equaling two different things, right? So draw this bracket, and it's equal to this linear function 6x minus 1 if x is less than 0, and then this other linear function 7x plus 3 if x is greater than or equal to 0. Okay, so part A, they want you to figure out what is f of negative 3. Okay, so if x is less than 0, you use the first 6x minus 1. Okay, and so our x here, our x equals negative 3, and that's definitely less than 0. So we're using the 6x minus 1 to do the evaluation. So I plug in negative 3 wherever I see x, and I get negative 18 minus 1 is negative 19. Okay, great. Let's do another f of 0. Okay, so this time our x value is 0. Okay, which is then greater than or equal to 0, right? So we're not in the first case, so because x is not 0 is not less than 0. We have to use the 7x plus 3 now, because x equaling 0 is greater than or equal to 0. It's in the second interval. Okay, so what do we have then? 7 times 0 plus 3. 7 times 0 is 0, plus 3 is 3. Let's look at another. F of 4. So this time x equals 4. So that's definitely greater than or equal to 0, right? So we're in that second interval, the 7x plus 3. Okay, so I'm plugging in 4 wherever I see x. 7 times 4 is 28, plus 3 is 31. Okay. What's a little harder then is graphing these things. So what I advise you to do is just to graph each piece separately over the appropriate interval. Okay. So part B in my notes here, part A is evaluating, part B is graphing. Graph each piece separately. So it's not like you're graphing two things at once, right? Graph each piece over the appropriate interval. Okay. Okay. So let's look at an example. We have f of x equals negative 1/2 x squared. If x is less than 1, and then 2x plus 1 if x is greater than or equal to 1. Okay, so I got two graphs. I have one graph when x is less than 1. So on the number line, here's 1, and I'm looking at everything below it, right? Maybe we'll think of it as an open dot right there. Okay, so for that case, I'm going to do maybe a little t-table, I guess. I'm using the negative 1/2 x squared piece. So we'll just pick up some numbers here, negative 4, 0. The numbers have to be in the interval, and I definitely want to use the endpoint here, this 1 value. Okay, so you see I'm using that value in my chart. All right, so I put in -4, I get -1/2 times -4 squared is -1/2 times 16, which is -8. And then I plug in 0 is just 0. I plug in 1, I get -1/2 times 1 squared is just going to be -1/2. Okay, and on the other side, and then x greater than or equal to 1, so on that interval, we're at 1 again, and we'll put a closed dot there, and it's everything above it. We can do a table. And here you want your first point to be that 1 value. Okay, so I'm going to use that first. And the other interval, I used it last. So you have to kind of evaluate it at the, you could call it the frontier between the two pieces. Okay, so I'm plugging in 1 here into this other function. So 2x plus 1, 2 times 1 plus 1, 2 times 1 is 2, plus 1 is 3. And let's just do one other point. 3, 6, 7, right? So 2 times 3 is 6, plus 1 is 7. Okie dokie. So finally then, I'll go ahead and draw my graph. Looks like I need to go down to -8, 2, 3, 4, 5, 6, 7, 8, and up to 7. 1, 2, 3, 4, 5, 6, 7. And I need to go backwards to -4, 2, 3, 4, and I need to go forward to 3, 2, 3. Okay, so at -4, 1, 2, 3, 4, I got -8, so that's down here. At 0, I have 0. And at 1, I have -1/2. And it's going to be an open dot there, okay, because of that less than sign. So if you have a less than, that's going to tell you the use. So I'm writing up to on the top right. If you have a less than symbol, that means an open dot. If it was less than or equal to, you would put a closed dot there. Okay, so if it's greater than or less than, greater than or equal to, or less than or equal to, closed dot, otherwise open dot. Okay, so right here at -1/2, I'm putting an open dot. And this graph is a parabola, so it's going to have that kind of parabola shape to it. Okay, sorry if I kind of screwed up the concavity, is what they call that right there. And then the other piece starts at, what do we got, 1, 3, and that's a closed dot, okay, because of the inequality is greater than or equal to. And then it's a straight line, so 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, looks like this. Okay, so those can be challenging, but just do it one piece at a time, okay? And you're graphing it. And you could even, draw the number line underneath and see, right here at 1, the first graph is that parabola that was from -infinity to 1, not including 1. And then the second graph is that straight line. So over top of that, over top of the x greater than or equal to 1, you get that other line. Okay? So you should have 2 separate graphs, at least in this case. You can have 3 graphs, you can have 4, just whatever they want. Okay, the next thing is on evaluating functions, but a particular thing that we're working with called the difference quotient. Okay? And the difference quotient is kind of a high-powered slope formula. Okay. But it's a slope formula that can be used with things that don't have straight lines on them. Okay? So in particular, remember the slope formula? So recall what the heck that thing looked like. Slope was y2 minus y1 all over x2 minus x1. You could write it, if you have a function instead, as f of x2 minus f of x1 all over x2 minus x1. Okay. That's kind of what we're working with here. It's not going to look like that, though. What it looks like for us is this, and you'll learn more about it once you get into calculus. But it really is just a slope formula. Okay. Okay. So that the h means a change in x. I don't know. I guess I could try to draw it out here. So we have f of x1, f of x2, this is x1, x2. f of x1, f of x2, and maybe we have some sort of thingamajig kind of going like this. This formula, the slope formula right here, basically finds you the slope of the line going from f of x1 to f of x2, okay? Regardless of what the function is. So the function, it could be even worse. It could be, something like this. But this difference quotient thing will kind of tell you the slope of the line going from x1 to x2. Okay, that yellow line is kind of the slope. So what the heck is that h thing? Well, what you're doing is kind of imagining that instead of x, you have x plus h. So we can kind of erase this, and let's erase this, and say that this distance here, and let's erase the little sub 1 thingamajig. Okay. So say this distance is h, so this will be x plus h, okay? And then you'll have f of x plus h. So if you plug that stuff into this slope formula, what do you have? We have f of x plus h minus f of x up top. That's just y2 minus y1 all over x plus h, which was x2, plus or minus x. Okay, minus x. So in the end, the x's cancel out in the denominator, and that's why it looks a little funny. Okay, it's not looking like the slope because it just has that h in the denominator. But I promise you, all it is kind of a new slope formula. And slope is just super important in math because slope represents rates of change, like rise over run, miles per hour, deaths per year. Anything you can imagine can be kind of described in terms of these rates of change, anything in the universe. Okay, and math tries to model the universe using this stuff. So this formula, this difference quotient formula, is very important to us. But at its bare bones, it's just a slope formula. So don't worry. If you're like me, I have a lot of anxiety. So if you're an anxious person, don't worry. It's no big deal. Okay, it's just slope. One thing to note, h can't be 0, can't divide by 0. Okay, so let's look at evaluating the difference quotient for particular functions. And to hit home the fact that this is a slope formula, we know, what is the slope of this formula, this function here? Well, it's 6, right? So our answer should be 6. Okay, so I need to evaluate this f of x plus h minus f of x all over h. Okay, so just do one piece at a time. First off, the f of x plus h part. So what I'm doing is putting x plus h in wherever I see x into f of x. Okay, so I'll have 6 times x plus h plus 1. Okay, so that formula there is this thing here, just with x plus h subbed into the formula. Okay, and then I go minus f of x. Okay, so f of x, all of x, f of x, not just part of it, minus parentheses 6x plus 1. Okay, so that is this thing. So f of x here is this guy right here. Okay, and then that's all over h. Okay, and then you're tasked with simplifying the heck out of this thing. And so let's simplify it, right? So first distribute the 6, so it's 6x plus 6h plus 1, minus distribute the negative, 6x minus 1 over h. And then what do we get? 6x's cancel, so I have 6h, and the 1's cancel, and then all over h. And then you simplify that, right? H over h is the same as 1 over 1. 6 times 1 is 6 over 1. 6 divided by 1 is 6. And just as promised, it is the slope. Okay, ain't that cool? All right, let's look at a harder one. Okay, so in this example, the slope is the quote-unquote slope is variable. And a variable, to find a variable slope, they call it taking the derivative. Okay, and we'll work with that once you get into calculus. Anyways, all you have to do for now is find the difference quotient. Okay, a little bit harder now because it's a more complicated function. So I want to figure out f of x plus h minus f of x all over h. And you don't have to memorize this formula. If it's on a test, I'll give it to you. All right, so here we go. F of x plus h. So I'm putting in x plus h wherever I see x. So I'll have some foiling to do there. Okay, so that first thing I just wrote was this. That's this. Okay, and then minus f of x, but all of f of x, so I have to put it in parentheses. Okay, so the second thing I drew out there, or wrote out, was just f of x. Right there. Make sure you put it in parentheses. Okay, so now I got some algebra, so this is great practice. Negative x plus h times x plus h. Let's maybe zoom in on that, so I'm drawing it out at the top right. Okay, so that's going to be x squared plus xh plus hx, which will just give me 2xh plus h squared. Okay, so this will be negative, parentheses, x squared plus 2xh plus h squared. And then distribute the negative 3, negative 3x minus 3h plus 1. Distribute this negative, plus x squared plus 3x minus 1 all over h. Okay, I'll distribute the negative in that first parentheses. Negative x squared minus 2xh plus h squared. I can cancel out these 3x squares and these 1s. So I'll have minus 3h plus x squared all over h, and the x squares cancel. And what do I have? Negative 2xh plus h squared minus 3h all over h. There's a common factor of h in the numerator and denominator, and I want to get rid of that. Okay, if you can, try to get rid of the fraction. It's not always possible in the homework, but in this case you can. So we can factor out an h. Negative 2x plus h minus 3 all over h. And then the h's divide out, so h over h is the same as 1 over 1. And you're left with just the negative 2x plus h minus 3. Okay. And then that would be the formula for your slope. Did I screw up the negative there? Oh yeah, I did. Sorry, there should be a negative right here. Okay, sorry about that. So this would be negative 2x minus h plus 3, sorry. Okay, let me sort of scroll over and see if there's anything to deal with online. What are we on, 1.3? Maybe take a look and see at some of these characters and see if there's anything I missed. Oh, this thing. So this thing is the floor function, kind of. Okay, let's zoom in on that. Okay, so you'll be required to evaluate it, and so for instance, I call up my page here, and give me some writing area. Okay, so this is a funny looking guy, and in particular, let's say I wanted to know what is f of 1.2. Okay. So at on the x point 1.2 on the graph, if you drew it out, it would be this part of it kind of looking. So 1 and then 2. And then here at 1, it's closed, and then it goes to an open. So what is that weird stuff meaning? It means it's kind of like it's kind of getting rid of the decimal. Okay, so in a weird sort of way. This one isn't as apparent. But f of 1.2 is going to be 0. F of 0.5, so 0.5, maybe I can get my different pen going. Maybe that would help. 0.5 is right here, right? In blue. So if you look up on the graph, that's going to be located at 1. So f of 0.5 is 1. So it's not really getting rid of the decimal. It's kind of, but you're always going to get an integer back is kind of what I'm trying to say. I can't get the stupid white pen back. I'm sorry. So this is 1. Maybe I should just delete this question from the homework, right? Just delete it. Let's take a look here. F of negative 0.2. So we'll have, maybe I'll put it in green. Negative 0.2 is about right here. And if you go up to the graph, that means you're going to be at positive 2. Okay. So what happens for like f of 0, right? If you go to the graph, there's an open dot. So f of 0, let me put that in like yellow, I guess. F of 0 is right here, right? So f of 0, it kind of looks like maybe it's at 2, maybe it's at 1. The open dot's at 2, so you don't use that. You have to go to the closed dot. So f of 0 is actually 1, okay? Okay, so let me see what they're after here. So they have the square root of some really bunch of nonsense. F of 0.3 plus f of 1.3 minus big parentheses f of pi squared plus f of negative 1 minus f of 2 times, whoops, minus, okay, so it's just this one thing, that's this one part of it is squared, minus f of 2 times f of negative pi. Okay, so f of 0.3, if you look over there on the graph, 0.3 will be 2. Okay, so this equals square root of 2 plus f of 1.3. 1.3 is here, so that's 0. Pi is about 3.14, right? So you go 1, 2, 3.14. So that'll go down to negative 2. And you're squaring it, negative 2 squared, plus f of negative 1 is 2, so there's a closed dot there at 2. F of 2 is going to be negative 1, so you go to the closed dot, so negative 1. And then f of negative pi, that's f of negative 3.14, it's about right here, so you go up to 5. Okay. Okay, so we have this equal to the square root of 2 minus negative 2 squared is 4 plus 2. Negative 1 times 5 is negative 5 times negative 1 is positive 5. So I have square root of 2. Negative 2 plus 5 is 3. Let's see if we got it. So I'm not going to write in an approximation. I'm going to literally write it in what I got. Okay, so plus 3, and hopefully that's the answer. If not, I am going to lose it, right? Check answer. Good job. Oh, come on. So I must have did something silly. I can't imagine they'd want. So f of 0.3 is definitely 1. Oh, that's what I screwed up. 0.3 is 1, not 2. So this is 1, this will be 1, this will be 1, and so 4. 4 is my answer. Let's try that again. I'm assuming it, just to be quick, I'm shooting from the hip here. Okay, so 4. Oh, dear heavens. Okay, so let me try it again. So square root of f of 0.3. So 0.3 is right here, so that'll be 1. Okay. Plus f of 1.3 is 0. Minus f of pi. So pi is 3.14. And that will bring me down to -2, but I square that, so it'll be 4 plus f of -1. F of -1 will be 2. Oh, it's a division symbol. Oh my God, really? So divided by f of 2 is -1 times f of pi, negative pi, which we said was 5. Okay, so let's try that again. That'll be square root of 1 plus 0 is square root of 1, which is 1, minus 4 plus 2 divided by -5. So you do division first. So this is 1 minus 4 minus 2/5. So this is -3 minus 2/5. Find a common denominator. So this is -15/5 minus 2/5, which is -17/5, and I'm thinking there's no way that's right, right? -17/5. Oh, Jesus, still not right. Okay, so let me try a similar exercise. Let's see how that goes. Let's see, I'm not having a good time. Okay, so this time square root of f of -2.8 plus f of, is that a division or is that a plus? My eyes are not what they used to be. I'm getting old. I am, if you're wondering, I am, how old am I? 47 now, I believe. F of pi squared plus f of -1. And then that's a division symbol, f of 2 times, oh, you have to do it, pi. I didn't do order of operations. I'm sorry. It's just one thing after another, you know. Square root of f of -2.8, so -2.8 is going to shoot me to 4. Hopefully 1.3 will be 0. Yeah, plus 0. F of pi, so 3.14 will give me -2, and then square that, that'll be 4, plus f of -1 is 2, divided by f of 2, which is -1, times f of -pi, which we're saying is 5. Okay, sorry, I didn't do order of operations, a little rusty. 4 plus 2 divided by -1 times 5. So order of operations, please excuse my dear Aunt Sally, where multiplication and division are always done from left to right. Okay, that was my problem. Okay, so and here I'm doing left to right. So square root of 4 is 2. I can just get rid of that. -4 plus 2 divided by 1 comes first. Right? 2 divided by -1, okay, is -2 times 5. And then you do the -2 times 5. So 2 minus 2 minus 4 minus 10. 2 minus 4 is -2, minus 10 is -12. Okay. And really, if this isn't right, I don't know what's going on. All right, so I hope you haven't lost all faith in your teacher. I do actually know what I'm doing. All right, so we'll see you next time. Okay, I'll just leave it there. All right, have a good day.